Hello and welcome to this Python tutorial. So in the previous section we implemented the PCA principal component analysis dimensionality reduction technique, which I remind is a feature extraction technique as opposed to the feature selection technique that we did in part 2 when implementing backward elimination. And now in this section we are going to implement LDA, which is another technique of feature extraction. So that means that from our original independent variables, which by the way are going to be the same as in the previous section, we are going to extract some new independent variables that will therefore reduce the dimensionality of our data set, of our problem, in a relevant way. So in the previous section, this PCA feature extraction technique reduced the dimensionality of our problem by extracting the variables that explain the most the variance, and now in LDA this is quite different. We are extracting some new independent variables that will separate the most the classes of the dependent variable. And therefore, since this time it considers the classes of the dependent variable, well, that means that it considers the dependent variable to proceed to this feature extraction technique, and therefore that makes LDA a supervised dimensionality reduction model, as opposed to PCA that was unsupervised, because we didn't consider the dependent variable and only the independent variables. Now we are looking to extract the independent variables that separate the most the classes, and the classes are informations related to the dependent variable, and therefore it is dependent variable related. So LDA is a feature extraction model, but this time supervised. And so now in this section we're going to work with the same business problem, and we're going to see if we manage to beat the accuracy obtained with PCA, that is 97%. In other words, we will see if we get a perfect accuracy of 100%, that is, we will see if we get no incorrect predictions. So let's start right now. Let's start implementing LDA, and actually this is going to be very easy, because basically what we'll do is take this PCA code that we just wrote in the previous section, because you're going to see that we will have very few things to change. So I'm going to paste it here, and you will see that we will execute the different sections one by almost changing nothing. So first of all, the data preprocessing phase, well, this is going to be the same as in PCA, because we just need a training set and a test set on which we apply feature scaling, and this is exactly what we do here in these 4 blocks of code, and therefore we can already execute that without changing anything. So let's do it, but before, let's not forget to make sure we have the right folder as working directory. So let's go to our folder, part 9 dimensionality reduction, and now we are in section 44, linear discriminant analysis, LDA. All right, now make sure you have the wine CSV file, and if that's the case, you're ready to go. So as I just said, we are ready to select these 4 sections without changing anything. So let's do it, and basically let's proceed to the first data preprocessing phase. Here we go, all done in less than 1 second. And now if I go to Variable Explorer, everything is ready. We have our original data set with all the chemical informations about the different wines and the dependent variable that contains the different segments of customers that this wine business owner could identify thanks to clustering. So perfect, let's press OK, and we have our training set that is scaled, but so far contains the 13 independent variables, the same as in the dataset, but scaled. And of course, what we're going to get is a new selection of independent variables that is extracted independent variables that this time are going to separate the most the different classes of the dependent variable that we cannot see here. So okay, that's for xtrain, and xtest, that's the same. We have our 13 independent variables that are also scaled. So pressing OK, and that's the same for the dependent variable. We have the dependent variable values, that is the different segments of customers 1, 2, and 3 for each observation that is for each one, depending on its information. So that's for the training set, and we have the same for the test set. All right, so data preprocessing phase done. Now let's move on to the next phase, which is about applying not PCA, but this time LDA, linear discriminant analysis. All right, and that's the same as for PCA. We need to apply LDA right after the data preprocessing phase, that is right after feature scaling, and just before fitting your classification model. It doesn't necessarily have to be logistic regression. It can be SVM or decision tree classification. But anyway, you need to apply LDA just before fitting your classification model to the training set. All right, so now let's take care of this section. Let's apply LDA. So first, there is no question of explained variance, so we will get rid of this line here because we're not looking for the independent variables that explain the most the variance. We're now looking for the independent variables that separate the most the classes of the dependent variable. That is our three classes: customer segment number 1, customer segment number 2, and customer segment number 3. All right, so now let's import the right class. This is no longer PCA, and this is actually no longer taken from sklearn.decomposition. This is now taken from sklearn.discriminant underscore analysis. Right. And then from this sklearn discriminant analysis library, guess what we need to import? Bad news, it's not LDA, but linear discriminant analysis. Here we go. So before it was LDA actually, but it was just changed into linear discriminant analysis. But that's okay, we'll be fine. And now we need to do the same as before, that is create an object of this linear discriminant analysis class. And so we're going to call this object LDA. And so this LDA object is going to be an object of this linear discriminant analysis class. And to make things more simple, we're going to add here as LDA and replace PCA by LDA. So that now we're creating an object of the linear discriminant analysis class that we just renamed LDA as a shortcut. All right. And then in this LDA class, well, we have the same argument, number of components, that is the number of, this time we call them the linear discriminants, as opposed to the principal components in PCA. So number of components, 2, which means that we take 2 linear discriminants, that is 2 new extracted independent variables that are going to separate the most the classes of our dependent variable. So this time actually we don't need to build a vector of explained variance or any other kind of vector like some sort of class separability vector. We will directly take n components equals 2, and we will already see with this if we get some good results. Because, well, since our goal is to actually get some independent variables that allows us to visualize the training set results and the test set results, well, we know that we're looking for 2 linear discriminants, and so what we're going to do is directly choose 2 linear discriminants, and then we'll see what we'll get, and mostly we'll see how it compares to PCA, where we chose indeed 2 components. Alright, and then we have these 2 lines here where we change our training set and our test set. By taking our LDA object, we're going to change that and then use the fit transform method to fit the object to the training set and transform it at the same time to extract the 2 linear discriminants so that xtrain becomes a matrix of 2 new features. And then we use the transform method on the test set so that same xtest becomes a matrix of features containing the 2 same linear discriminants. However, we need to change 2 things here. First, of course, we need to replace PCA by LDA. So that's obvious, LDA. And then we need to do one more thing here. Can you guess what it is? Well, it is related to the fact that LDA is a supervised model, and therefore, when we transform our training set, the matrix of features xtrain, well, since we also need the information of our dependent variable ytrain, because we are looking to separate the most the different classes of the dependent variable, Well, we also need to include yTrain in this fit transform method. And so now that is in this specific input of the fit transform method that we clearly see the difference between a supervised model where we include the dependent variable yTrain and an unsupervised model where we only include the matrix of features xtrain. So that's the key difference between the two: unsupervised model for PCA and supervised model for LDA. And then in the transform method, do you think we need to include yTest? Well, no, because yTrain is just used here to fit the LDA object to the training set. And by fitting, I mean understanding the structure of the training set and the relevant informations to achieve our goal to extract the independent variables that separate the most the classes, and these required informations are contained in yTrain. And then, since here we just transform xtest using our fitted object, well, we don't need to fit it again, and therefore we don't need the informations of ytest. So that's perfect here. We just need xtest, and therefore we're ready to apply LDA to our dataset. So let's select these 4 lines here and execute. Here we go. Perfect. LDA correctly applied. So now remember, before xtrain and xtest contained 13 independent variables, and now we can already see that they contain 2 independent variables that are the new extracted linear discriminant independent variables from this LDA feature extraction technique. And of course, these new independent variables are scaled. So pressing OK, perfect, and same for xtest. The same 2 independent variables. All right. So now we are ready to fit the logistic regression to the training set. We're going to keep this logistic regression model because we are interested in comparing the performance results that we obtained with PCA to the performance results we're about to obtain with LDA. So we're going to keep this logistic regression model, and let's hope that we can beat PCA by obtaining an accuracy of 100%. That is, no incorrect predictions. And by the way, since LDA is looking to separate the most the classes, well, we expect that the classes will be perfectly well separated, and therefore, if that's the case, we should get an accuracy of 100%. That depends on how the dataset is structured, but we should be pretty confident. Alright, so now let's fit logistic regression to the training set. We don't have anything to change here, everything is already ready, and so I'm going to select this section and execute. Perfect. Now our logistic regression model is built on the training set that is only composed of 2 independent variables that are our linear discriminants. Great. Now let's move on to the next section. Let's make the test set predictions. So again, we don't have anything to change here. That's the beauty of the template. Pressing enter, executing, yPred vector of prediction ready. We can click on it, and here we have all our predictions. So the first one is predicted to belong to customer segment number 1. Second one of the test set is predicted to belong to customer segment number 3, and third one of the test set is predicted to belong to customer segment number 2. So let's see now in the confusion matrix if we get no incorrect prediction. That will be pretty exciting to see because it's at this right moment that we'll know if we beat PCA. So again, everything ready here. I'm ready to execute. Pressing enter. Here we go. Confusion matrix ready. Let's have a look. And here we go. No incorrect predictions. As you can see, we have all zeros here, 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 and here. And all our correct predictions are here. And indeed, our test set contains 36 observations. And here we have 14 plus 16 equals 30 plus 6 equals 36 correct predictions. We don't even have to compute the accuracy. We get an accuracy of 100%. That's great, and actually that was not totally unexpected because this perfect 100% accuracy results from the perfect separability of our classes. And the perfect separability of our classes results from the goal of LDA that indeed extracted the independent variables that separate the most our three classes 0, 1, and 2. That is customers number 1, 2, and 3. Alright, so perfect. Let's press OK. We can now have a look at the training set results and the test set results, but we'll get perfectly well separated prediction regions, and the prediction boundary will be kind of the same as PCA, but we'll do a better job at separating the classes. So let's have a look. Actually, we can do some minor changes here. It's of course to change the X label and the Y label PC1 and PC2 and replace them by LD1 and LD2. So let's do it quickly. LD1, LD2, LD1, and LD2, and now we're ready. We don't have any more thing to change. We have our three colors corresponding to the three classes, and therefore we are all good. We are ready to select this whole section here and visualize the training set results. Alright, so that's the training set results. As we can see, the prediction boundary is slightly different from the prediction boundary obtained in the previous section with PCA, because we can clearly see that each straight line composing this prediction boundary is separating well the red points here that correspond to customer segment number 1 to the green points here that corresponds to customer segment number 2. Indeed, we can see that if we take the closest red points to this prediction boundary straight line, and same if we take the closest green points to this same prediction boundary straight line, well, these red points are approximately equally distant to this straight line as these closest green points here. So that's by definition of class separability. But then if we look at the prediction boundary between the blue region and the green region, corresponding to respectively customers number 3 and 2, well, we can see that this class separability is less obvious when we look at these closest green points here and this closest blue point here. Well, that's actually just due to the fact that these points were considered as outliers by the LDA model, and therefore the LDA model rather considers these points here and make them equally distant as these points here from this prediction boundary. So that's interesting, and same if we look at the class separability between the red class and the blue class, well, that's the same. We can see that this prediction boundary straight line here is actually equidistant from the closest blue points here and the closest red points here. So basically, if we don't consider the outliers here, well, this LDA model made a perfect job at separating the three classes. So great. Now let's have a look at the test set results. So again, nothing to change here. We are ready to visualize the test set results by just executing this. Here are the test set results. And so again, the three classes are well separated, and we can clearly see the results that we obtained in our matrix of confusion. That is this number of 0 incorrect predictions, because indeed all the red wines are in the red region, all the green wines are in the green region, and all the blue wines are in the blue region. So that's perfect. Each wine is in its correct segment of customers, and therefore this wine business owner can feel pretty confident at predicting for each new wine to which customer segment he should recommend it. And not only he can be pretty confident at recommending the new wines to the right customers, but also thanks to the feature extraction technique that allows him to visualize its results in 2 dimensions, thanks to this number of 2 new independent variables, the linear discriminants. Well, now this wine business owner can make a clear plot of its different segment of customers and putting in each segment of customers the different wines. So eventually that can be pretty convenient. Okay, so perfect. We managed to build a great LDA model, so we'll finish on this good note, and therefore we'll move on to the next section of this course, which is going to be another feature extraction technique, but this time adapted for non-linear problems. So since this problem is obviously a linear problem, because we managed to apply very successfully linear models as PCA and LDA, as well as the logistic regression model, which is also linear, well, it won't be relevant to apply a nonlinear feature extraction model on this dataset. So we will work on another data set that is of course going to be nonlinear. And this next new feature extraction technique that we're going to see is going to be kernel PCA. So I look forward to starting this in the next section.